Okay, here we have an LRC circuit, and we have a source that doesn't look like a direct current source. It's generally not going to be a direct current source. It is kind of interesting what happens with the direct current in a circuit of this case, but it's even more interesting what happens if you have a voltage that varies in some way. Now, I've kind of indicated a sign variance here, but this could be any kind of a variance. So this is a variable source, and maybe I ought to label it as such. A variable voltage source. Okay, so here's a variable voltage source. Now, it turns out that the voltage change as you move around a circuit has to be zero. This is a result of the fact that the electric field is conservative in nature. So, if we travel around the field through these wires and devices, if we travel around the circuit through these wires and devices, then we're staying within an electrical field. It's continuous throughout. And it follows that by the time we get back here, we've done zero work. If we carry a charge around here, we've done zero work due to the conservative nature of the field. Now, voltage being work per unit of charge, that means that the voltage change around the circuit is zero. So that the voltage of the source, turns out, has to be equal. Well, okay, you move across the source, your voltage increases. If you move across any of these circuit elements, your voltage decreases. Now I'm being a little, I've got a diagram up here, I'll come to it in a minute. This gives us the equation: voltage of the source is voltage of the resistance plus voltage of the inductor plus the voltage across the capacitor. And the voltage across the resistor, as we've already experienced in lab, is current times resistance. Okay, because we have Ohm's law, voltage equals current times resistance. Voltage drop is a current times the resistance. Voltage across the inductor, as we said in the previous, or as we showed in the previous clip, is the rate of change of the current multiplied by the inductance. Okay, and the voltage of the capacitor is voltage, or is charge over capacitance. Now, this doesn't look much like a differential equation, except we do have a derivative of I, and we have I, but then we got this Q thing, and Q is also varying in time according to all the factors that influence what kind of voltage there is across the capacitor, what kind of current there is through the capacitor. Well, the capacitor, you're basically moving charge from one plate to the other, one way or the other, one direction or the other, so that the current is the amount of charge that's being moved per unit of time. Current then is the derivative of the charge in the capacitor with respect to time, so that current is Q prime. I'm going to switch to primes just for compactness of notation, so that IR becomes I dQ dt times R, which is R times Q prime. Di dt is the derivative of I with respect to t. I is dq dt, so that di dt is the second derivative of q with respect to t. So we have a term where we have the second derivative of q multiplied by L, and that's our L q double prime term. And then we have our q over c term, and now we have a non-homogeneous second order constant coefficient differential equation. L is constant, R is constant, C is constant, so reciprocal of C is constant. And this is all equal to our voltage source. So this is non-homogeneous because we have a voltage of the source. Now, of course, that voltage could be zero in some instances. But we have the equation, and everybody's had this chapter, and I just completed this chapter in the differential equations course, or in the process of completing it, so we know how to solve this equation. At least we know what the techniques are, so we're going to work through that. Okay. Now, just one quick thing about the signs of these voltage changes and so forth. Let's just consider a situation that you will have already seen in lab. You have a voltage across a resistor. So you're measuring voltage across the resistor. Let's just say that the voltage here is higher than the voltage here, which should be the case if you have a positive here and a negative here. So let's say this voltage is 4 volts, and the voltage over here is 2 volts. Okay? So we have a negative 2 volt change as we go across here. Well, if the voltage here is 2 volts, there's no resistance here, so there's no voltage drop. So that the voltage here is 2 volts, and similarly here, the voltage has to be 4 volts between these 2 points. So as you go around the circuit, you have a drop from 4 volts to 2 volts, and you come down to here, and then you have a rise from 2 volts to 4 volts. Now this is just to establish, and don't worry about how these numbers came about. All we're establishing is if this is at a higher potential than this, then as you go around the circuit in the counterclockwise direction, you have a voltage drop here and a voltage rise here. So that the voltage rise is equal to the voltage drop. The change in voltage here is equal and opposite to the change in voltage here, but if the change in voltage here is negative, then your voltage drop is a positive number. So we're saying that the voltage drop across R, this voltmeter is measuring the voltage drop across R, or the voltage increase across the source. Okay, because attaching the voltmeter here and here is no different than attaching it here and here. We could attach it halfway between if you wanted to, but it doesn't matter. Every point on this wire is at the same potential, and every point on this wire is at the same potential. And that leads to the equation where the voltage of the source is equal to the voltage across the resistance, etc. The voltage change across the source is equal and opposite to the voltage change across the resistor, inductor, and capacitor, and that's exactly what this equation is saying.